Hey everybody, welcome back. We're starting chapter 8, and we are now going to do something that we haven't done before, and we are now going to integrate with respect, instead of to the x or y axis, we are going to integrate with respect to a curve, some sort of function, and that can be a function of x or a function of y. And of course, when you hit third semester calculus, you'll have even an option for more variables, multivariate. And so before we get started, I want to kind of show a little bit of the theory behind what it is that we're doing. And I want us to picture we have some sort of generic function. Some sort of y equals f of x situation. And what we want to know is how far is it to walk from point A to point B along this curve. So what we want to know is how long is that? That is going to be our L. And what we're going to do is break that up into little tiny delta S's. And let's talk about our delta S here for a second. What I'm going to do is I'm going to zoom in closer and closer and closer and closer and closer until I see that delta S actually is a straight line. Kind of like on Earth, when we look out, it looks like the Earth is flat, but in reality, we know that it's a giant sphere, but we're so close to it, it looks flat. And here I have my delta X and my delta Y, which means delta S squared is going to equal delta X squared plus delta Y squared, which means delta S is the square root. We're going to assume it's positive, so I'm not going to do the plus or minus. Delta X squared plus delta Y squared. And what I want to do is I want to factor under the radical a delta X squared out. And we're there, and we end up with and you can see that if I take delta S and I shove it down to 0, making it an infinitesimal, that we have ds is the square root of 1 plus dy over dx squared dx. And what we're actually going to be doing is adding all of those up. So our L is going to become, from A to B, let's add them all up, the square root of 1 plus dy over dx. And we'll see in a minute, dx over dy may apply when we have a different setup for the function. And that all comes from adding up along L ds. And that's going to be a recurring theme here, adding up those ds's as we're adding up along the curve there. That brings us to the beginning of the lesson, our formula that we have. And this is what I just derived here. Showed you kind of why and where that comes from. And we're going to get started. And what I like to do specifically is work on that inner piece there. So I'm going to take y prime, I'm going to square it, I'm going to add 1, then take the square root, and then see where we can go from there as far as an integral goes. So y prime is going to be 3/2 x to the 1/2, y prime squared is 9/4 x, 1 plus y prime squared, which brings us to our formula integral, and we're going from 1 to 4. Root of 1 plus 9/4 x dx. And here's how, this is how we build that up. Sort of our scratch work off to the side here. I'm now going to do a substitution. And there's my dx. We're also going to have to convert the boundaries. I'll get to that in just a moment. So this becomes u to the 1/2 power du with the 4/9 out in front. That's from here, the conversion. Now the boundaries, I got to plug into here. So when I plug in 1, that gives me 9/4 plus 1. That gives me 13/4. And when I plug in 4 here, you can see the 4's cancel, and I get 9 plus 1, which is 10. So here we have our fully converted integral. And this becomes 2/3. I'm doing the power rule here. U to the 3/2 from 13/4 to 10. And when I plug that in, multiplying that out, I get 8/27. And when I plug in 10, I get 10 to the 3/2 minus 13/4 to the 3/2. And that can probably be cleaned up a little bit more, but we're just going to stop there for now. So we get the idea. The tricky part is doing that, finding that conversion from the ds to the dx, or in this next case, dy, if I can introduce the next one. So if we have a curve that is x as a function of y, and y goes from c to d, then g prime, we're assuming g prime is continuous on c to d, then we end up with our new formula. It's not that new. Everything just gets switched out. Dx over dy squared dy. So you can see it's pretty much the same formula as before, but now we're doing everything in terms of x as a function of y. And we have our example here. See there. And we have that, that y squared is equal to x from 0 to 1. Now, in reality, that is going to be a sideways parabola. And if I have that x equals y squared, then dx over dy is 2y. And now I'm just going to build that out there. Dx over dy squared is 4y squared. And 1 plus dx over dy squared is 1 plus 4y squared. So there we have our piece. So we're going to end up with the integral. Now we have x goes from 0 to 1. And when we need to know the y version of that. And here, okay, so here's where it gets a little weird. When x equals 0, y also equals 0. And when x equals 1, y also equals 1. We actually end up with plus or minus 1. I'm going to add a piece here. I'm going to say that y is positive in this case, so that we're just going to deal with the top half of the parabola and not the bottom half as well. And we end up with the square root 1 plus 4y squared dy. There's our integral. And what we're going to end up with is a triangle. And 2y and 1 square root of 1 plus 4y squared. And I'm going to notice that the tangent of theta is 2y, which means dy is 1/2 secant squared theta d theta. What I did was I divided the 2 and then took the derivative. So there's my dy. There's one piece. And now I'm going to notice that the secant of theta is the square root of 1 plus 4y squared. And when I put all of that together, and unlike the previous one, I'm not going to convert the boundaries. I'm going to go all the way back to y when I'm done. So I'm just going to leave those blank for now. But I need to know that this ends up being that, which is secant theta, times that. So we get a 1/2 secant cubed theta d theta. So there's my secant theta times my secant squared theta to give me the secant cubed theta. There's the 1/2 d theta. And I derived integral of secant to the third in a previous video. And that gave us 1/2 secant theta tangent theta plus 1/2 natural log of secant theta plus tangent theta. And again, we don't have the boundaries, but I'm going to convert these both back to y, and I'm going to do that using the triangle. And I'm going to distribute that 1/2, so 1/4. Secant theta times tangent theta plus the natural 1/4 now, right? Distributing the 1/2. The natural log of secant theta plus tangent theta. And all of this is going, we're now back to y, so that's from 0 to 1. 0 to 1. Looking good. Now, I'm just going to deal with this first one here. When I plug in 0, the whole thing goes to 0. When I plug in 1, here, 1 squared is 1, times 4 is 4, plus 1 is 5. Root 5 times 2. Now, once again, when I plug in 0, that's gone. When I plug in 0 there, I end up with square root of 1, which is 1. Natural log of 1 is 0. So that 0 turns all that into 0. So when I plug in 1, I end up with root 5 plus 2. So my final answer ends up being this here. Now, I know that's a hideous looking number. Oh, that was absolute value. That's right. But there you have it. Not too bad so far. Let's see what else we have. All right, we have another x is a function of y. And I'm going to modify that real quick and say that x is equal to 1/3 y to the 3/2 minus 3 y to the 1/2. And again, all I did was distribute the root y, which is y to the 1/2 power, of course. All right, so I'm going to go ahead and take the derivative of that with respect to y. Just using power rule. I'm going to notice that if I distribute the 1/3 in there, those two 3's go away, and I have a 1/2 in front, so I'm going to actually factor out a 1/2. And if I square that, 1/2 squared is 1/4. And I end up with y to the 1/2 minus y to the negative 1/2 squared. Let's actually work that out. When I square that, apply the binomial squaring rule. And now I'm going to add 1 to that and distribute the 1/4 all at the same time. So 1 plus, I'm going to distribute that 1/4. 1/4 times 2 is 1/2. And I can see that I can combine up 1 minus 1/2. Gives me a positive 1/2. And once again, I can factor out a 1/4, just so that it matches here. That's what I'm trying to do, actually. And you can see that is exactly the same as that, but I have a plus instead. So instead of minus there, it's going to be plus. And if I do the square root, I end up with that there. Yeah, ran out of space there. So what's going to happen is that L is going to be 1/2, that's from there. The integral from 1 to 9. So they very nicely gave me the values in terms of y of y to the 1/2 plus y to the negative 1/2 dy. And very nicely, I now have power rule again. And now I can just drop that 9 in and drop the 1 in. And I'm going to go ahead and distribute the 1/2 as well. And you can see the 2's will cancel there. So 1/3. And I'm going to get 9 to the 3/2 minus 1 to the 3/2, which is 1, plus square root of 9 minus square root of 1. And that is square root of 9, that's from the 2 is 3. 3 to the 3rd is 27. And here I have 3 minus 1. That's 26 over 3 plus 2, which gives me 32 over 3. Not so bad. You just have to really kind of focus and kind of keep track of what you have and what you need and all that kind of stuff. I'm trying to get everything in one frame. I'm missing out just a little bit. There you have it. And this last one, problem here. What we're going to do is I'm going to rewrite x times y equals 1 into y equals 1 over x. So I just divide both sides by x. I can do that because x is not going to be 0, so we're okay. And they're only asking for the setup on this one. So we're just going to get to the integral. So y prime is negative 1 over x squared when you rewrite it like this. Because you subtract 1 and bring the negative 1 down to the whole deal. And y prime squared is 1 over, that makes it positive, x to the 4th now. So we're there. So my integral for the arc length is going to be the square root of 1 plus 1 over x to the 4th dx. And this one just wants the setup, so make sure you read the directions. a lot of teachers, this is a common thing to do. They're less interested in your integration skills at this point, since you just went through chapter 7, and more about the setup skills. So I really hope that that helps out.